If you need to search a massive system log for an error, you have a problem. The target word might be capitalized, entirely lowercase, or mistyped as error by a frustrated developer. Searching for an exact string will miss most of these variations. We need a way to recognize patterns. On the left, we are typing a basic regular expression using a character class. By placing A and E inside square brackets, we tell the system to accept either letter as a valid match for that single position. Looking at our document on the right, the command successfully highlights both gray and gray, while entirely ignoring gritty. We can scale this logic up. Entering a range like 0-9 instantly targets every number in the document. If we insert a caret at the front of the brackets, the logic flips. This tells the system to exclude characters. Here, it filters out all the vowels, leaving only the consonants. Character classes act as flexible nets. Instead of forcing you to predict exact spellings, they define the acceptable parameters for a single slot of text. This forms the baseline logic for all UNIX text processing. Character classes handle variations in a single position, but real-world data is messy. You will frequently encounter unknown word lengths or entirely unpredictable characters trapped between known letters. Look at the visual breakdown here. The dot acts as a wildcard that matches exactly one of any character, so C.T catches cat and cut. The asterisk operates differently. It is a quantifier that means 0 or more of the immediately preceding character. So CA*T matches cat, cat-a, and even CT, where the A is entirely absent. If you are used to the standard UNIX command line, pay close attention. In regular expressions, the asterisk is not a general wildcard on its own. To match literally anything of any length, you must combine the two operators. As you see here, dot asterisk allows Datiron to bridge the gap and capture the entire word coat. Up to now, we have focused on identifying specific characters. However, the physical location of the text on a line is often the most important factor in a search. Watch this mock file. We use line anchors to pin our search to specific positions. The caret anchors the pattern to the exact start of a line, grabbing the word the only when it begins a sentence. The $sign anchors it to the end, isolating the word end right before the line break. Combine them directly, the caret immediately followed by a $sign, and you match an empty line. Regular expressions are highly effective at finding the absolute absence of data, giving you a quick way to strip blank space out of configuration files. The basic asterisk is useful, but its leniency causes false positives since it allows for 0 occurrences of a character. For tighter constraints, we move to extended regular expressions, which we activate by adding the -e flag to our grep command. This chart shows how extended operators refine our control. While the asterisk allows anything from 0 to infinity, the plus sign strictly requires 1 or more occurrences. The question mark takes the opposite approach, capping occurrences at a maximum of 1. In the terminal, running CA plus T against the string CT yields no result. The plus operator actively filters out this text because the required A is entirely missing. Now look at the question mark applied to the U in color. It successfully returns the British spelling, but the question mark makes that U strictly optional, meaning it will also match the standard American spelling color. Let's test this. Pause the video and write an extended regular expression that will match these 3 specific variations of the word kitchen: kitchen with an E, kitchen with an I, and kitching with an ing. Here is the solution. We start with the shared root kitch. Then we use parentheses and a pipe to create an alternation, accepting either E or I as the middle vowel. Finally, we add N and apply the question mark to a grouped G, making the ending consonant optional. By deploying extended operators, you replace broad, messy searches with highly targeted extractions. Let's put everything together in a single command. Our final goal is to extract 3 specific words from a text file: heard with a capital H, heard, and heard. First, we address the capitalization. On screen, we open our pattern with a basic character class containing both an uppercase and lowercase h, covering our 2 starting states. Next, we handle the varied middle vowels. We expand the syntax with an extended regex alternation group, defining our 3 acceptable paths: EA, E, or I. Finally, we append the static ending -erd. When we execute this full command, it isolates heard from the input while remaining perfectly primed to catch the other two variations. This table summarizes the core symbols. We have our character classes for specific options, the dot and asterisk for open-ended matching, the plus and question mark for strict numerical constraints, and our positional anchors. Memorizing this syntax gives you absolute command over your operating system. It allows you to process, filter, and reshape raw UNIX data exactly as you need it.